It is the first building at the entrance of the Academy of Science and Technology. So I will be in charge of the lecture of this course, and in the tutorial class, you will be working with your tutorial teachers, Miss Tang or Miss Nguyen, the two. Okay, so according to the to ESPH, you will be divided into 9 groups to do tutorial groups. And I'm not sure if the tutorial groups will start this week or next week. And, anyway, you will be working. I will be in charge of the lecture, and you will work with 2 other teachers in tutorial classes. About the course, we will have 9 weeks of in total 18 hours of lectures and 18 hours of tutorial. Okay. The content of the course will be divided into 2 main parts. Counting or enumerative combinatorics, and some introduction to graph and tree. So the first part, the counting part, will be the bigger part. It will occupy from 6 to 7 lectures, and we will have some very basic introduction to graph and tree. And if you follow up to in applied mathematics or in ICT, then you will have more advanced courses on graph theories. Okay, so now the main part of this course will be on different various counting techniques and some combinatoric problems. Okay, about the final mark of the course, you will have 10% of attendance, but to be honest, I don't know how we count it. So basically, if we continue this online format, then perhaps you will have full attendance mark for free. So let's say that you have bonus 10% attendance mark, then you will have 30% of we call it partial mark, but it may be a combination of assignments and tests. Maybe assignments only if we keep doing this online format. It is not for it depends on the convenience. So we may do some assignments, or we may do some tests, and we take the average, we multiply it with 30%, and finally, of course, there will be a final exam which will be accounted for 60% of your final mark. And in order to pass this course, you will have to achieve at least 10/20. Okay. So I hope it is clear for you. Is there any question about the mark or about the format of the evaluation? If not, then we can move on to the content of the course. Okay, so this course will be based on the this group of Kenneth Rosen. The title of the book is Discrete Mathematics and its Application, and we will use specifically the 7th edition. So you can easily find a PDF copy of this book when you do a quick Google. Okay, so I will not provide you with the full book. Nevertheless, I uploaded the relevant chapters on Moodle. So if you if you don't want to have the full books, then you can download the chapters that will be used in this course on Moodle. So specifically for the counting part, we will use materials in chapters 6 to 8 of the book, 6 and 8. So chapter 7 is about probability, and we will not talk about probability. We have only 9 weeks, and perhaps you will have more detailed courses on probability later. Okay, so chapter 6 and chapter 8 for the counting part, and chapter 10 to 12 for the introduction to graphs. Of course, we will not use the entirety of, oh sorry, maybe I should activate the record to the cloud, I think.
Recording in progress.
Okay, so recording in progress. Okay, so for the introduction to graph part, we will use some basic material in chapters 10 to 12. Okay, so if you visit the Moodle page now, you can see the chapters and the slides of today's lecture uploaded on Moodle. So I will update the Moodle page in parallel with our progress in the course. Okay, so I will upload the list of exercises later. Okay. So is there any question about this part, the general information of the course? Okay, so if there are no questions, then we will proceed to the content of the course. Okay, so as I said in the part on general information, in the first part and the bigger part of this course, we will deal with counting problems. So as you may be aware of, counting is one of the most basic mathematical operations. Okay, so you learn to count even before you learn to do additions or subtraction, etc. Okay, so counting may be considered the most basic operation of mathematics, but it is not easy. It is basic, but it's not easy, especially in the context of today's development in information technology, in computer science, etc. Okay, so basically the counting problems aim to answer the question how many. Okay, so basically you have some in mathematical language, you have some sets, some finite set of objects, and you want to know how many objects are there in that set. So for example, in engineering, maybe when you design something, you will, in order to optimize your design, you need to know what is your what is the demand, and what capacity of the system you design should be in order to be able to cope with the demand, but without wasting too much resources. For example, if you are charged with determining the length of telephone numbers in the country, then you have to you have to do some sort of study to know the population of the country and to estimate how many telephone numbers you will need. And after having an estimate of the numbers of telephone number that you need, your system needs to support, then you will decide the length of telephone numbers in order to have enough numbers for let's say the people in your country. But you of course you can always use very long telephone numbers, but it is not practical. It is the longer the numbers, the more difficult it is to remember them or to store them, or maybe for the operations will be more complicated. For example, if you want to look for some specific number in a database, then a database of long numbers will be larger and will make your search more time consuming. Okay, so recently in Vietnam, you may encounter the problem of determining the length of ID numbers. Okay, the personal ID numbers. So in order to determine that, we will use 11 digits for is it 11 or 12? I don't remember. Okay, so basically, in order to determine the length of ID numbers or the length of social security numbers, etc., or the length of bank ID, so you have some. You will need to have some kind of estimates of the size of the demands, and then you have to design something that is enough for that. But you also have to optimize so that your system is not overloaded. Okay, in computer science, I don't know if maybe some people in ICT may have heard of complexity of algorithm. Okay, so what is an algorithm? An algorithm is a procedure, a design in order to solve a specific class of type of problems, or maybe to calculate something. Okay, to automate the calculation of something. For example, you may have heard of search algorithm, or in or handwriting recognition algorithm, or AI algorithms. So there are a lot of algorithms that are talked about nowadays. But when you will study algorithm, you will know that there is an important aspect of algorithm that you need to investigate when you design algorithms. That is called the complexity of algorithm. So without going into details about the exact definition of complexity, you can roughly understand that the complexity of algorithm will give you an estimate on the efficiency of the algorithm in terms of time of execution. So the bigger the complexity, the more time your computers will need to execute the algorithm. But in order to estimate the complexity of algorithm, you will need to be able to estimate the number of calculations that will be carried out when you execute when you execute an algorithm. So counting problems play a very important role in the estimation of complexity of algorithm. And complexity means efficiency. Okay, so similarly to the problem of determining the length of telephone numbers, you may have the problem of estimating the size, the storage you need. Maybe if you are an engineer working in a data center, you will need to know how much material, how many hard drive, what is the capacity of hard drive you need in order to run the server or in order to store your database. Okay, so you need to have enough storage, but you don't want to buy too much, to spend too much on material, because it may cost you more money. Okay, and of course, when you calculate probabilities, we will not. When you calculate probabilities, there are a lot of counting involved. Basically, if you calculate some kind of probability, you need to count the total number of possibilities. Okay, the total number of outcomes, and then you count the total number of outcomes in your interest. Then you take the you take the letter and divide it by the formula, and you find the probability. Okay, so here I give you a puzzle. So maybe some of you have heard of this puzzle. It is called the birthday paradox. So in the puzzle form, it is a question that asks the following. Okay, so you know that your birthday can be one of the 365 or 66 days of the year. And the question is that, what is the minimum number of students in the class? Assuming that the students have the students' birthdays are random dates, random. Okay. So what is so the question is that, what is the minimum number of students in the class, so that the probability that two of them have the same birthday is larger than 50%. Okay, of course, here in this class you are close to, you are more than 350. So it is very close. So it is not interesting in the context of this class, because you are so numerous that the probability that two of you in this class share the same birthday is close to 1. But you can carry out this experiment in the in a smaller tutorial class, and to say, and if I don't remember the exact number, but it is around 30. You will already have probability roughly 50%. So we will go back to this puzzle, and once we have seen all the basic principles of counting, we will be able to give an answer to this puzzle. Okay. So just a little remark. If I have a habit of speaking quite fast, so if during the lecture you have there is anything you don't understand, do not hesitate to raise a question, or to ask me to repeat, or to explain more slowly what is on the slide, or about what I am talking about. Okay. So if you don't interrupt me, then I will assume that everything is okay. You understand everything. Okay. So if you want me to re-explain or to explain in more detail about something, then please raise your hand in Zoom so that I can stop and pay attention to your question. Okay. So just wait a minute. I will go back and we will delve into the basic principles of counting. So here you can, as you can see on the slide, we of course there are many techniques to count, but here are the most here are the building bricks, the most basic principle upon which we will derive more sophisticated techniques that we will see later in the course. Okay, so here we are in today's course. I will introduce to you 4 principles of counting, namely the product rule, the sum rule, the subtraction rule, and the division rule. Okay, so let me go and fetch some water, and then I will go back to talk about product rule. Okay, so can you hear me? Hello?
Yes, we can.
Okay, so let us begin let us start getting acquainted to the product rule by the help of an example. So this one is a very simple example. Okay, so you can read it here. It says that we are interested in counting the numbers of seeds in a filter. Okay, so if we are given the information that the seeds in this filter are labeled differently, okay, by and the label will be in the format of one English letter followed by a number from 1 to 50. Then what is the maximum number of seats that there can be in this theater? Okay. So here you have something like you may have some seats labeled A02 or B13 or E17. Okay, so we may have seats like seats with labels like that. Then the question is how many seats are there if we use each label exactly once. Okay, so if every label is used, then you have the maximum number of seats. Okay, so without knowing about combinatorics, I guess most of you have already have the answer, which is 26 multiplied by 50. Okay, so here 26, it is the number of letters in the English alphabet, and 50 here is the the number of integers from 1 to 50. Okay, so but why is it multiplication here? So here, let us break down the reasoning here. So when at the start of counting problems, even if the questions are easy, I would like you to develop the habits of breaking the counting objects into procedures. Okay, so here let us think that we have to count the number of labels, and in order to count, if each label is an object, then we will think about a way to create such a label, such an object. Okay, so here we will write a general label in this form. So it is a letter from A to Z in the English alphabet, followed by an integer from 1 to 50. Okay, so you can think that in order to create such a label, we have to create the letter part and then the digital part. Okay, so in order to create the letter part, we will have to choose a letter from A to Z, and since there are 26 letters in the English alphabet, we will have 26 choices for the first part. And then, of course, in order to pick out a random number from 1 to 50, we have 50 choices or 50 possibilities. And here, the multiplication, we use the multiplication here, and you will see that it is by the product rule. Okay, so here in the full solution of this example, we break down this counting problem into 2 steps. Okay, so these are the 2 steps in order to create an object of interest, an object that that we want to count. Okay, so the first step is to choose the letter, and the second step is to choose the number. So note that these 2 steps are carried out in a sequence. Okay, so you do the first step followed by the second step, and then you multiply the number of ways to do the first step by the number of ways to do the second step, and you get the results. And so here, is it clear?
Yes, it's clear.
Oh, so this example is very easy, but what is new is the way of thinking. The way, as I said, I would like you to think of counting at to break down the counting problem into a sequence of steps in order to create an object of interest. Okay, so here on here. Right. Okay. Okay, so on the next slide, you have the general statement of the product rule. Okay, so here it is stated in an abstract way. So you want to count the number of some objects, and suppose that you can give a procedure that is used to create such an object, and that procedure can be broken down into k sequential steps. Okay, so they are k steps, one followed by each other, by one followed by another. Okay, so here we suppose that there are n1 ways to do the first step, n2 ways to do the second step, and so on, and until nk ways to do the last steps. Then the product rule states that the total number of ways to carry out all those steps, so to carry out that procedure, is equal to the number of ways to do step 1 times the number of ways to do step 2 times etc. times until the number of ways to do the last step. Okay, so here the key so the keyword here is sequential. That is, you do the steps one after another, as illustrated in the picture here. So here, suppose here we have, this is the step 1, this is step 2, and so on until step k. So this you will see this diagram more in probability, but here it is used to illustrate this this rule. So if here the first step you have n1 ways or n1 possibilities, and for each way or each possibility of in the first step you have n2 ways possibilities in the second step, then you can continue, and then at last you will have n1 times n2 times etc. times until nk ways to do the whole thing. Okay, so this formula is a way to write this rule in the language of sets. Okay, so you are, if you don't do computer science or mathematics, then it is not mandatory for you to know this formula, but this formula may be useful for those who are more familiar with math, with sets or math symbols. Okay, so for the math people, you can retain this formula. Okay, so otherwise you can you can think of this picture. Okay, so we will illustrate this rule by further examples on the next slide. Okay, clear drawing. Okay, so here is a question, an example in computer programming. Okay, so maybe nowadays you don't have to worry about memory and stuff, so this may not be familiar to you, but back then, maybe 20-30 years ago, we didn't have unlimited memory, so programmers back then, the old school programmer had the habit of being very economical when it comes to managing memories, and even the names of variables or the type of variables, because you need some, you always need some kind of storage or some memory space in order to store the value of a variable. Okay, so here, back to this example, let's say that in a program you have a variable which is stored using 7 bits. So this is a very low-level programming. Okay. Then, if this variable is stored in 7 bits, then how many values can there be? So you can think maybe you have some variable used to index the some object or some data. So if the index is stored in 7 bits, then how many indices can there be? So here, if you haven't known yet, a bit stands for binary units. So in computer science, a bit is a value of 1 or 0. Okay. So here in computers, the numbers and text and everything is stored in strings of zeros and one, which are called bit strings. Okay. So here you have 1, 2, 3, 4, 5, 6, 7 bits to store a variable of in this program. Okay. Do you know about the binary systems, binary number system? Hello?
2.
Yeah. Okay, so for the ICT and applied math folks, maybe yes, but for do you have students in biology or something? CS, ICT, what is DS? Okay.
Data science.
Okay, so we have people from other departments too. So, okay, where is the slide? Okay, so here is the, so for example, if you have, I will use well, okay, so here, for example, if you have 110 here, then it is similar to our decimal system, except that for each position to the left is the value associated. Each unit of the position to the left is twice the value of a unit in a position to next to it to the right. For example, here this 0 here means 0 times 2 to the 0. Okay, so this one here gives a value of 1. 1 is the digits, and 2 to the power 1. And this one here gives 1 times 1 to the 2. Okay, so this here in base 2, this binary number is equal to, so here we have 4 plus 2 plus 0, that is 6 in our normal notation. Okay, so here, for example, this variable, if and two values are different if at least 1 bit is different. Okay, at the same position. So here, in order to count the number of values that can be stored using these 7 bits, we will break down into a procedure just like we did with the previous example. So here, we will go from left to right or from right to left, as you like. So here with our lots of generalities, let's say that we go from right to left. That is from the position with the smallest with less value to the position with greater values. Okay. So here in the first position, in order to, we have two choices, 0 or 1. Okay. So here we can have either 0 or 1. We have two choices for this position. Okay. So we have here 0 or 1. Here you also have 0 or 1, and so on. So for every position, you have two choices. Okay. So here, our procedure consists of 7 sequential steps corresponding to 7 bits. Okay. So according to the product rule, the total number of ways will be equal to 2 times 2 times 2, 7. There are 7 factors. Okay. Or in other words, there are 2 to the 7, which is 128 different values. So if you want to use the notation of the definition, then in this case, you have 7 steps. Carry is equal to 7. And for each step, you have two choices. So n1 is equal to 2, n2 is equal to 2, and so on. So n1 times n2 times etc. times until n7 is equal to 128. Okay, so it's easy, right? Is it easy? Okay, so now let us look at something more which appears more complicated. Okay, what is the number of subsets of this set? Let us consider the set of the first n integers, namely the numbers 1, 2, 3, etc. up to n. Suppose we have such a box that contains these numbers. Each number appears only 1, and we want to take out a subset of numbers from this set. Then how many ways are there to form such a subset? Of course, I'm sure that some of you know the answer. But now, what I would like you to do is to arrive at that answer using a reasoning based on this our product rule. Okay, so maybe I will give the answer here. Spoiler, it is 2 to the power n. Okay, it is the number of subsets of a set of size n. But how do we achieve this result using the product rule? That is, how can we derive a procedure to construct or to create a subset of this set, which consists of a certain number of steps, and then we use the product rule to multiply the number of ways together. Anyone want to try? Okay, so if no one wants to try, then I will give the answer here. And it turns out that why this looks different No, it's not n factorial. It's 2 to the power n here. So why? In order to have a clear explanation of this result, we will, as stated in the product rule, we will have to derive a way to construct or to create such a subset. So here, of course, if you think of it in a naive way, then a subset of this set of size n may have 0 elements. The empty set may have 1 element, 2 elements, and so on. So if you look at it that way, then you can see that the number of elements in a subset in some subset, in all the subsets are not the same. So it may be at first glance it is not intuitive to have some procedure with a fixed number of steps, but I can think of it this way. Suppose that our subset is a box here, and we line up the numbers from 1 to n, and we will go through these numbers one by one. Okay, and for each number we will consider whether we put it in our subset or not. Suppose that this is a subset. Okay, so for each number we will look at that number and we will answer the question: does this number belong to this subset or not? So for each number we have two choices: yes or no. Okay, yes, it belongs to this subset, or no, it doesn't belong to this subset. Okay, so you go through these numbers one by one, and for each number there are exactly two ways to answer this question. So for the number one, there are two choices: yes or no. For number two, there are two choices: yes or no. For three, there are two there are two choices: yes or no, and so on. For n, and here you have n times 2. So it will give you 2 to the power n. Okay. So yeah, I have seen one answer in the chat, but in fact, yeah, that's true. That is an identity, but that identity may be considered a corollary of this result. Okay, so it is cheating too. So in fact, in order to we will go back to that identity, but that is I don't consider that a proof, because in order to prove this one, if you use something that is itself a consequence of this one, then it is not valid. Okay, so in order to Nguyễn Hoàng Gia Lâm, in order to prove your identity, you have to use the fact. Of course, you can use induction, but another proof is you have to admit the fact that the number of subsets in this set is already 2 to the power n. Okay, so it is not it's not sound logically. And anyway, we have this. I prefer this way to use the product rule to prove this result, because it is simple. It is a very basic tool, and it is intuitive. Okay, so if you remember this product rule, you only have to remember that you look at the numbers, all the numbers. For each number, you decide yes or no. For each number, there are two possibilities. So in total, there will be two to the power n possibilities. Another way to look at this is that you can relate this example with the previous example by identifying each subset with a string of 0 and 1. Okay, so you can imagine that you can in some way encode each subset of this set S with a string of length n. Okay, so you use n bits to encode subset. So how? For the first bit to the left, if it is 0, then the number 1 does not belong to the set. Okay, so let's so here at the second position, the bit is 1, so that means that the number 2 is in the set. Okay, so bit so in that way you can you can identify each subset of this set with a binary or bit string of length n. And according to the previous example, you can generalize this example to n. Okay, so here for 7 bits you have 2 to the power 7. So of course it's exactly the same for n bits. You will have 2 to the power n. And so if you identify each subset with a string of bits consisting of zeros and 1, and 0 if the corresponding number does not belong to the set, and 1 if the corresponding number belongs to the set, then the total number of subsets of this set will be exactly the total number of bit strings of length n, which is 2 to the power n. Okay, so the solution is resumed, is sum up here on the slide, so you can look at the slide later at home. It is available on Moodle. Okay, okay, here another question for the computer science folk. Okay, so here sometimes in your program you have to have embedded loops or nested loops such as this one. And here, if you have some algorithm like this, then in the analysis of algorithm, you maybe have to count the number of elementary operations that your program carry out. Okay, so suppose that your algorithm has some nested loop like this, then what is the number of operations executed by this nested loop? Okay, so of course here the question is a little different. You have some variable k to which you assign the value 0, and then you for each iteration of the loop you increase the value of k by 1. And of course, if each iteration increments the value of k, then starting with 0, the final value of k will be equal to the number of iterations of the loop. Okay, so this is one way to look at, to analyze the efficiency of your algorithm. Okay, so here you can think that each iteration in fact correspond to a set of value I1, I2 until IM, okay? Because for each value of I, so here you can see for I1 taking a value from 1 to N1, I2, so for each concrete value, each specific value of I1, I2 until IM, you will have one execution. So in fact, in order to count the number of iterations of this nested loop, you have to count the number of n tuple, the number of such collection of values of I1 to IM, such that I1 is from 1 to N1, I2 is from 1 to N2, and so on. So here, if you can once you have identified the number of iterations with the number of such n tuple values, then of course you can use a similar procedure as to the previous example to count. Okay, so here you have an n tuple of values. You have n1, yeah. So, yes, correct. Okay, so here you have your procedure will consist of choosing a value by the first step will be choosing a value for I1. The second step is to choose a value for I2 and so on. So for I1 you have N1 choices, for I2 you have N2 choices and so on. So by the product rule you multiply the number of choices for each individual step together. Then you get this final answer. Okay. So you can see that there are many of the 8 examples given here are related to math or computer science, but in the exercises you will have some more example maybe related to DNA sequences, the ways of arrangements of objects. Okay. Okay, so that's the last example of the part on product rule, and we will now proceed to the sum rule. Okay, so here for the sum rule, I will give you the definition first, and then we will look at some example to illustrate the definition. Okay, so here, similar to the product rule, in order to count the number of objects, we have to have some procedure to create such an object. But here, the procedure is not sequential, but the procedure here consists in choosing one of k choices. Wait a minute. Okay, so here is the picture. So here you can see that in the picture that illustrates the product rule, you have a sequential procedure. One step is followed by not the steps, but here the steps are not the steps, but the choices are, let's say, independent of each other. Okay, so you can either choose this branch. You can either choose this to do your task or to do your procedure, or this, and suppose that all the ways, all the choices are different from each other. And then, of course, you can guess from the picture that the total number of ways to do this task is equal to the sum of all these numbers, n1 plus n2 plus etc. plus nk. And for those who want mathematical language, then you can look at it such as this. And for other folks, it is not mandatory, but if you are interested, if you can use this one, then it's better. Then that's good for you. Okay. Now, okay, let's look at this example. We have an example similar to the previous example, the previous subsection. Okay, so it looks rather similar. We also have some kind of loops. Okay, we have m loops, very similar, but the difference is that these loops are not nested. So these loops are out of each other. Okay? So here, similarly, you start with value 0 for the variable k, and for each iteration of each loop, you increment the value of k. Okay. So this question, what is the final value of k, is in fact, what is the total number of iterations of all these loops? Okay. But here, since the loops are not nested inside each other, the result will be different. Okay. Yeah, exactly. Now, okay, so here you can think of it this way. So here you can see that we only enter the second loop after the end, the termination of the first loop, and at the end of this here, that k is equal to n1. Okay, and at the end of this loop here, we have taken this value k equal to n1, and we increment it n2 times. So here the new value will be this value here, n1, plus the number of iterations, okay, and so on. And each time we add the number of the new loop. So here you have n1 plus n2 plus n. Okay, and a little remark for Chu Baoming. If you do computer science, then you will not write n1 equal to k, because you have to write k equal to n1, because their roles are different. K is a variable and n1 is a value. Okay. No, BI, what is BI? BI is informatic or something. Yeah, you always write the variable to the left. Otherwise you will mess up your program, the code. You should be careful, even in the small details. Okay, so you get the answer. The final value will be the sum of all these. Okay. Of course, in this course, you will not be writing code in this course, but if you continue to do things in ICT and apply mathematics, then maybe it's a good thing that you develop the good habits as early as possible. Okay, so here, this is a more complex example in which we will combine the product rule and the sum rule to get the result. Okay, so here suppose that a very archaic, a very ancient forum use outdated technology, and so so the usernames in that forum can only be some string of length between 6 and 8, okay, and can only contain alphanumerical characters. Okay, so here you have lowercase letters or digits, so it is not even case sensitive. Okay, so here suppose that you have such a forum, then what is the upper bound? What is the maximum number of username you can have in the database of this forum? So here you can see that if we break down this problem, if we will find a way to create to construct a username for this forum. Okay, so we have so here we use the first step is we have to choose the length for the username. So your username can either be 6 character long or 7 character long or 8 character long. So here for 6 character you have 1, 2, 3, 4, 5, 6. Seven. Okay. Okay, and for each of these branches, we need to count the number of available usernames, valid usernames. Here, there are no further constraints. There are no forbidden words. There are no rule except that all the characters should be an English letter or a digit. So you can also start a username with a digit. Okay, so here, how many choices are there for each position? You know that we have 26 letters plus 10 digits. Okay, so we have for each position we have 26 available characters. Okay, so here we will for each branch is a familiar question. We already know that here we have 26 to the power 6. Okay, so here in the second branch we have we have 26 to the power 7, and here you have 26 to the power 8. Okay, so inside each branch you use the product rule, and then you combine the 3 branches using the sum rule, and you get this result. And let us see what is the answer here. Okay, so that's the answer. So even with this restricted outdated setup, you have this total of roughly 3,000 billion available username. Okay, so largely sufficient. But of course, these are in this we have included every possible string, and if we limit to the usernames that somehow makes sense, then maybe there are fewer available usernames. But here, if you are willing to, if the user are random spam bots with random usernames, then you can have these are enough. Enough. Okay, the 10 here is the number of digits. You have the digits from 0 to 9. Okay, so here is an example of combining the product rule and sum rule. And in fact, these for the short exercises, you will only have to apply directly the product rule or sum rule. But this rule, why seeming simple, can prove to be useful in a complex counting problem. But so you can see here that here we have a two-step counting problem. You have to break down the procedure of creating a username into two steps, and then you apply the rule in each step accordingly in order to find the result. Okay, so the basic rules, the basic things are always simple, but it is the combination that are powerful. Now let us apply some restriction to this example. Okay, so you have a similar setup, but you are interested in the usernames that contain at least one digit. Okay, so previously you can have you can have usernames that are letters only. Okay, so here you want to eliminate all the usernames which are letter only. You are interested in the username that in which there is at least one digit. Then if you in other words, if you take a valid username at random, then what is the probability that there is some digits, one or more digit in it? Anyone has an idea how to solve this? So this is a simple probability question, but in discrete probabilities, we may have to do many counting problems. Okay, we have two different answers here from Đoàn Hà Nhi and Vin Mạnh Hà. Okay, and another one, approximately. Okay, so your answers are more or less the same. So here, yeah, you're correct. If you think in the naive way, then maybe you will count the number of usernames which contain of length 6. So if we apply a naive reasoning, then you have length 6, length 7, length 8, and in length 6 you have 1 digit, and 2 digits, and so on until 6 digits. In length 7 you can branch into 1 digit, 2 digits until 7 digits, and similarly in 8. So if you do it this naive way, then it works. It works, but even then, there is some complication that you don't have the tool to resolve yet. So here we have a more clever way. We have a more clever trick. That is, instead of counting the number of user names that have 1 digit, 2 digit, etc., we will count the reverse. So we will count the number of usernames that have 0 digits. It may be easier for us to count. So if we don't accept any digits, then there are only 26 choices left for each position. Okay, because there are 26 letters. So we combine all the cases of length 6, length 7, and length 8, and get this result: 26 to the 6 plus 26 to the 7 and 26 to the 8, which is roughly 200 billion usernames not containing a digit. Okay. So we take the previous results, that is the number of valid usernames that contain at least 1 digit is the result on the previous slide minus this number. Okay. So we have, and then you take this number divided by the total here, and we still get a very large percentage, which is more than 90%. Okay, so the answer, 55% of Vietnam is not is quite off the mark. Okay, so you can see that it is rather counterintuitive, right? Or maybe or not, or maybe not. Okay. So of course you have, so here let's see what is the annotation. Okay, so here of course you have on the one hand 26 letters, and you have only 10 digits. Okay, so maybe at first glance you may think that since there are much more letters than digits, the probability that there is at least 1 digit maybe not that large. Okay, but it turns out that in probability sometimes the intuition is not correct, and it turns out that the probability that a random word consisting of letters and digits of length between 6 to 8 has a very large chance of containing at least 1 digit. even if here you can see that the ratio of digit to letters is quite small. It's done roughly is just a little bit more than a quarter. Okay.
But teacher,
Yes, please.
how do I figure out the usernames that containing at least one digit?
Okay. So we will. So that's a good question. So we will go. In fact, here we have cheated a little bit because it is the next rule, a particular case of the next rule, the suppression rule. Okay, so in fact, you have maybe it's better to see it in a picture. So here you have the total of usernames. Okay, you have this is the set of total username, and inside this set you have username that have here that 0 digits. Okay, if you divide and here you have up to at least one digit. Okay, so in order to count the number of usernames with at least one digit, you will take the complementary. Okay, so do you agree that the whole space of username can be divided into two separated subsets? One contains usernames with with no digits. Okay, maybe two. No digits. Okay, so here are the usernames that have at least one digit in it. Okay, so in fact it is the reverse of the sum rule. Sometimes you can see this is called the complementary rule. So what is complements? Or in Vietnamese, cần bù. Okay. So here it is very often that it is a quite common technique to count the complements instead of the set of interest. Okay, so here we know the total number, and but if we want to count the number of usernames in this part directly, it may be complicated, but it turns out that it is much simpler to count the number of usernames in this part. So so we can. So it's easier. It's more convenient to count the number in this part, and then take the total minus this number to find the number, the remaining number of usernames in this part. Does that answer your question?
Yeah, okay, maybe.
Okay.
Maybe I understand.
Okay, so you will see it better in after some exercises, the tutorial class. Okay, so a subtraction rule here is given by this picture, and this picture is taken out of the book of Rosen. You can see it in the book. I forgot to put the page number here. But essentially, it says that when you have two sets, you know that in the previous case, in the sum rule, we have our choices are separate from each other. So when when we have separate choices, then we can take the sum. But what if we have, for example, two choices, but the choices are not separate, but overlap each other? So it is exactly this situation here. So this is this is expressed in by this formula in the set, the language of set. Okay, so here, let's say that you have two possibilities, but they are not separate, or they are not disjoint. There is some overlap here. So from this picture, it is rather obvious that the total size of this here are in the language of set, the union of the two sets, the size of this H shape here is equal to the size of each circle, the sum of the sizes of the two circles. But here, if you take the sum of the two circles, then the overlapping part has been counted twice. Okay, once in A and once in B. So you have to remove the excess. Okay, how to okay, so here I will give you another explanation. So here, let's call this part here the part that is A only. So here is equal to A only plus. So here, this notation here, the vertical side of the two sides here means the cardinality, or the size, or the number of elements of this set. This is the number of elements in A. This is the number of elements in B, or in short, the size of A, the size of B. This is the size of the union of A and B, and this is the size of the intersection. Intersection means this overlapping part here. So if you so A union B is equal to A only plus B only plus overlap. Okay. So the left-hand side is equal to this, and the right-hand side, if you write A as A only plus overlap, then the right-hand side is equal to A only plus overlap. Okay, this is A. Plus B is equal to B only plus overlap. Okay, but if we stop here, then you can see that on the right-hand side there is only one overlap, but on up to here we have two overlaps. So overlap has been counted twice here. So we need to remove the existing overlap. So that gives us this identity. Okay, so you can look at the picture and you can imagine, you can let's say that you can map the size of the set as the area of the circles here. Okay, so you can see that the total area of this H shape is equal to the area of the left circle plus the area of the right circle minus the overlap part, the area. Okay, here this is the Venn diagram. This is the Venn diagram. But what we are interested in is the number of elements in these sets. Okay. Okay, so let us look at the example. Okay. Oh. Okay. So here we have another example on counting the number of bit strings or binary strings. So suppose that we look at the bit string of length 8, okay, and we want to know how many of those start with 1 or end with double zero. Okay, for example, we want to know, so this one you can have 1 0 0 0 1 1 0. Okay, so this one start with 1 here, or you can this one so this one end with 2 0. Okay, so of course with help of the product rule, you are now suppose that you should be able to count the number of bit string in the first category or the number of bit string in the second category. But when you combine the two, there is a problem, because, for example, this guy here, this string belongs to both categories. So you have 1 here, and you also have 0 at the end. So in order to eliminate the overlapping cases, we will have to use the subtraction rule here. Okay. So here you know that if you fix 1 at the start, then you have 7 free positions. So here you have 2 to the 7. Okay, and in the second case you have fixed 0 at the end, and you have 6 free bits at the start, and in this case you have 2 to the power 6, and the combination of these two cases, here you have 2 to the power 5. And if you would like to reproduce the Venn diagram, then here you have the 1, here you have the 0, and in the middle you have the 1 1, something in the middle. Okay, okay, so here So here's the diagram. You have 1, 2 to the 7 here, 2 to the 6 here, and 2 to the 5 in the middle here. So in total, you have 2 to the 7. That means 128 plus 64 minus 22, which will give you how many? What is it? So it should be 160, right? Okay. So that's how you apply the subtraction rule to solve a simple counting problem. Okay. Okay. So here the solution here. It is rather compact here, but if you like, and I encourage you to draw the Venn diagram to illustrate this the simple problem like that, and then once you are familiar with, when you have master it, you can do it without. But in the beginning, it is better to draw a picture to understand more intuitively. It is 2 because we are look at binary string. Binary means there are only 2 values for each position. Okay. Oh, thank you. Thank you. People who answer. Okay, there are, I don't know, 5 minutes left. So I guess we okay, the division rule is used when there are repetitions in our counting. Okay, so here is the formula where it's a mathematical formula. Okay, in terms of sets. So suppose that we have we have counted n ways in total, but during the counting procedure, we have counted each object multiple times. Okay, so think of this. You can you have found A, and then but you are interested in counting each object exactly once, of course. So if you have overcounted things, so similarly to the subtraction rule, in the subtraction rule, you have counted the the overlapping part twice, so you have to remove the excess. So here it is similar, but it applies to multiplication and division instead of addition and subtraction. Okay, so here suppose that you have counted n times in total, but during the counting procedure, you have counted each object d times. Okay, so of course you have overcounted the object. You have to compensate by dividing the result by d. Okay, so here suppose you have n. Okay, so let us go directly to the example. You will see that in action. Okay, so this is a classic example of the division rule. You have the question that if you have at the meeting, if we shake hands with each other, or in the COVID time we don't shake hands, we use the elbow bump or fist bump, then how many fist bumps or elbow bumps are there in total? Okay, suppose we have n people in a meeting. So here we will count. We will first use the product rule to count the total number of elbow bumps. Okay, so you will use, you can think of it as the product rule or the sum rule. Okay, so basically we will look at the number of elbow bumps that each person make with another person. Okay, so here, so each person will fist bump with n minus 1 others. So we have each person has n minus 1. Okay, so in total, since there are n people, there will be, of course, n times n minus 1. But here's the trick. One elbow bump or fist bump, okay, one fist bump is made by 2 people. Okay, so this elbow bump is counted twice. One for this person and one for this person. So here, according to the division rule, since each has been counted twice, we will divide the total by 2. Okay? What is the simple U square? Okay, let me see it. So here, this symbol is the disjoint union. Okay, the union you already know, but this sign say that it is the union, but these sets A1 to AK are disjoints, or in other words, are separated from each other. They have no common element. Okay. First, do we have class after that? After this?
No.
Okay. So the last example. Okay. So here, each person will meet or will shake hands with. So each person will shake hand or will fist bump with n minus 1 other people. Okay. So according to the product rule, if you count the total number of fist bumps of all the n people, then you have to multiply this amount by n. Okay. Okay. But here is the each fist bump involve two people, so that when A meets B, so this fist bump is counted twice, as once for A and once for B. Okay, but in fact, it is only one fist bump. AB or BA are the same, but here, since we have counted every fist bump of every person, we have indeed counted this pair twice. So in order to find the correct number, we have to divide the total by 2. So that is the meaning of the division rule. If you overcount something multiple times, then you have to divide by that multiplicity. Okay. Is it clear for you?
Yes, it's clear.
Okay, thank you. So I think that we don't have time for the pigeonhole principle. Okay, so we will continue next week with the pigeonhole principle. So I'm not sure. I haven't been confirmed with the department whether you have a tutorial class starting this week or next week. But either way, I will upload a list of exercises on Moodle by tonight. So if it is this week, then you can start working from tonight, or if it's next week, then even better. Okay. I don't know where the records are saved. I will, but I will ask the school to see if you can access this record somewhere. Okay, so here we are 5 minutes over the time, so I will stop the recording.
Recording stopped.
Okay, so are there any questions? You can use Moodle to send me messages if you have questions related to the course, okay, or related to the lecture. I will try to reply within 1 day. To my device. No. I chose save to cloud. So it should be available somewhere on the internet. I chose record to the cloud, but I don't know where the cloud is. I don't know. I don't have experience with Zoom. With Google Meet, I know with Google Meet, then it will be saved to my drive. I know it, but with Zoom, I don't know where it is. But maybe it is because this meeting was created by the department, so maybe it is saved in the account of the USDTH. Okay. So I will ask them and I will get back to you later. Okay, so see you next week. Okay, stay safe, eat healthy, sleep, eat and sleep well. Keep yourself from getting COVID. Okay, and see you next week.
Okay, so will there be any assignment for this week?
I will upload a list of exercise in the book. In the book, there are plenty of exercises. So I will provide a list, not all, and the assignment will be decided by your tutorial teacher. Okay.
Okay.
Bye, teacher.
Fine. No. Bye, teacher.
My teacher.
You again.
Teacher.
Bye,
Teacher, see
Bye,
you.
teacher.
Bye,
Bye,
teacher.
teacher.
Thank you.
Goodbye, teacher.